All right, so welcome back. So any questions up front? Like I said, I'm going to talk about Lab 2. I'm going to talk about some more stuff about K-maps and product of sums and stuff. But questions up front, we can talk about them right now.
So, like, for question 11, you said that we can still do the SARS part of the question, but not the K-map.
No, I want you to do the K-map. You don't have to do the SAR part.
Okay.
Because we haven't really discussed SAR.
So I was looking at question 11,
Mm-hmm.
and the way that it's written kind of confuses me. I'm not sure which part is SAR and...
Well, the goal is to find a minimum sum of products, right, for this equation. And so the MD term, those just means those are don't cares. So the terms, the values for F corresponding to minterms 9 and 11 are don't cares. But the original question says, right, find the minimum sum of products using a K-map and then find the minimum sum of products using SAR. So just ignore those last two words, right, and just obtain a minimum sum of products for the following Boolean function using a K-map. That's the question I want you to tackle.
So the MD 9 and 11, those are like the dashes then?
Those are the dashes, exactly.
Okay, gotcha.
All right, well, let's run through an example from Lab 2. Let's look at this experiment number 2, switch usage, and let's look at how to put this schematic together, because experiments 3, 4, 5, you're given the chip, you're given the pin numbers, right? That sort of has already figured out the wiring for you. But let's talk about how you go from a schematic like this to actually building a circuit. So I have a copy of that schematic over here. And let's take this and try to transcribe it to TinkerCAD. Okay? So the first thing is we have these inverters. And somewhere in the lab or in the discussion in the book, right, you should figure out that an inverter is a 7404. So I'm just going to label these like U1. They're going to come from one chip, which is going to be a 7404. And by the way, you'll see these things sometimes referred to as 74 LS04, a 74 HC04, sometimes just a 7404. They're all basically the same thing. So way back in, I believe it was the 70s, Texas Instruments, company in Dallas, came up with a whole set of these chips. There were inverters, that was a 7404, there were AND gates, which was a 7408, and so on and so forth. And they released these, and they became kind of the standard for when people wanted integrated circuits. They were always numbered this way. So 74 was the type of chip it was. It was a digital chip for commercial use. And then the thing after 74 was which chip it was. Okay, so if you go to the following website, engrcs.com, okay, so it's the same page that you find the schedule on, but don't say /schedule, just engrcs.com. That's the engineering computer science website, okay? And on the left side of that, there's a thing that says component specifications. If you click on that, you'll see a list of all these different chips available. Now, you won't see a 74 HC04, which is what TinkerCAD has, but you see a 74 LS04. Okay? These letters in the middle basically say what kind of 7404 is it. LS is called a low-power Schottky device. HC is something else. Different ways of building the chips, but the behavior of the chip is basically going to be the same. So if you click on this, you get what's called a data sheet. And every chip comes with a data sheet, right? So this actually came from Texas Instruments. And there's a little sales blurb in the front here: dependable Texas Instruments quality and reliability. That doesn't tell you anything about the chip, right? That's just their marketing department. So there's a description: these devices contain 6 independent inverters. Okay, now you have to match up the device with the part number. So 7404, 74LS04, 7404 with nothing in between. These are all this chip up here. Okay. There's another set of chips called 54. There's a 5404, a 5408, and so on. Different chip. Okay, remember this number in the beginning is what type of chip it is. 74 is the standard commercial grade digital devices. 54 is what are called mil-spec devices. And the mil-spec devices, they can handle more vibration, they can operate at a higher or lower temperature, they can handle higher humidity. They're made to be more rugged. They're things that you would put into space, for example. And they have a different pinout, right? In particular, the ground goes over here and VCC goes over here. And you can also get these chips in different packages. Here's a flat package, which sits, lower on a board, and it has a whole bunch of pins on it, right? 20 pins, 5 to a side. This is how you hook this thing up. So you have to know what the part number is, right? And that'll tell you which diagram to pay attention to. So we're paying attention to this diagram up top, which tells us ground goes on pin 7, VCC goes on pin 14. And then there's these pins labeled 1A, 1Y, 2A, 2Y, 3A, 3Y. And if you scroll down, you'll see a picture of 6 inverters, and the A's are the inputs and the corresponding Y's are the outputs. And it tells you the function performed, Y equals just the complement of A. So if we want to use an inverter from this package, we can go in on 1A, come out 1Y, which means we can go in pin 1 and come out pin 2. Or we could go in pin 3 and come out 4. Or we could go in pin 13 and come out pin 12. So if you have a schematic like this, and you know you want an inverter, and you figured out that's a 7404, next thing to do is figure out what pins to use. Okay, so I'm just going to start off with the first inverter. I'm going to go in pin 1, going to come out pin 2. So I'm going to label this. I'm going to put a 1 right here and a 2 right here. And then my next inverter, I could use any of the remaining 5, so I'll just go in on 3 and I'll come out on 4. So I'll label this 3 and I'll label this 4. And I'm also going to put a note where I need to put my power and ground connections. And go back to your data sheet. Ground is on pin 7, so I'll put a 7 here. And power VCC is on pin 14, so I'll put a 14 under there. Alright, switches I don't really need to label pins because there's only there's only 2 connections to it, right? But if I want to switch like this, right, I'm going to connect to this point and that point. If you actually flipped over the switch, you'd see 8 pins on the back, 4 pins here, 4 pins there. So this point of the switch and this point of the switch, they're controllable by sliding this little slide switch up and down. Okay, so I might label this like, switch 1, just to remind me I'm using that leftmost switch. Resistors just have 2 ends, we don't have to label those. L1 and L2, those are LEDs. Okay, and if you look at the lab, there's a picture on the first page saying how these LEDs are wired. The straight wire goes to ground, the bent wire goes to positive. Okay, so I'm going to put a little note on my diagram here. Now this is not a standard notation, this is just for me. The straight wire goes to ground, so I'm going to label this end with a little straight line and this end with a bent line. And this back end of the LED is the one going to power, so I'm going to label that with a little bent wire. And I'm going to label this side with just a straight wire. right? And that's my LED. Again, this is not standard notation that you would use, but I'm just going to doctor this up as I build a circuit to help me keep track of what I'm building. Alright, I think that's all the information I need here. 7404, I'm going to make 4 connections to that, connect up power, ground, and then build up switches and stuff. So let me pull my TinkerCAD over, and let's create a new circuit. And I'll call this lab 2. What experiment is this? Experiment 2. Yeah. So I'll call this lab 2 experiment 2. Oh yes. Okay. So sorry, I'm reading my chats now. So the apostrophe on a variable is saying an inverse. So when you have a with an apostrophe after it, that's just a bar, which is also tilde a. Yeah, so people already answered that in chat. I don't need to answer it. All right, so let's go ahead and build this. Okay, over here on components, click that and say all. That's how you get all of your chips and all the good stuff like that. And let's find what we need. I'm going to pull a breadboard over. I think a small one will be big enough for this. I'm going to need a power supply, so I'll pull that. And we're going to need a 7404. So all the way down to the bottom, hex inverter 74HC04. And we're going to need a dip switch. So dip stands for dual inline package, DIP. And it means that there's a line of connectors on one end and a matching line of connectors on the other end. Alright, we're going to need 2 LEDs. And we're going to need 1, 2, 3 1K resistors. This should say 1 kilo ohm. So I'm going to pull 3 resistors out, and I'm just pulling things out of my parts box right now. You can go directly from the edge to the board, but I'm just pulling these out just so that I have them. And then I can make that go away, so I've got more space. Alright, so let's wire up our power lines first. Okay, so the usual drill. Let me put the power supply on the side. And let me run some wires. So I'll go from here over to ground, make that black, straighten it up, go from here over to power, make that red, straighten it up. And then I'm going to connect my power lines to the top of the board also. So that's a ground wire, and here's a power wire. Make it red. Alright, so we've got power. Let's put the chip down here. And I don't know where the best place is to put it. I'll just put it here for now. I'm going to put my switch over here on the left. And I'm going to use this leftmost position here. Okay, so I'm going to use switch 1. Let me bring it over just a little bit. Alright, I'm going to start marking my schematic as I build things. So I want one end of my switch to go to ground. I'm going to do this wire right here. So I'll just take a wire from here, connect it to my ground line. And I'll go ahead and color code that black. Okay, so I've done this wire right here. I want the other end of the switch to go to a 1K resistor, and I want that 1K resistor's other end to go up to power. So I'm going to take a 1K resistor, and I'm going to drop it in here. And so now the other end of the switch goes to one end of the resistor, and the resistor goes up to power. Okay, so now I've built this. I'll put that wire up to the 1K, and I put that up to 5 volts. Okay, so this part is done. All right, from here I want to connect to pin 1 on my chip. So let's just run a wire. So this point right here, this is where the resistor meets the switch, right? So that's this point right here. That's where the resistor meets the switch. Let's just go ahead and run a wire from there over to pin 1. And I don't know a good way to make these wires neater, which is kind of unfortunate. I wish I could bend them the way I can bend the wires out here. But anyway, so we've got a wire from the connection between the switch and the resistor to pin 1. So we've got this done. If you have a highlighter, highlighters work well, but I didn't have a highlighter. So I'm just filling those in. All right, so the output of the inverter, pin 2, should go into the bent leg on the LED, L2. So let's put L2 on our board. And I'll put it on the right, to say that it's L2. And so the output of the inverter is supposed to go to the bent leg. Okay, that's the positive side. So that's this wire right here. Output of the inverter goes to the positive end of the LED. And then I want the negative end of the LED to go to a resistor and go to ground. Alright, so here's the negative end of the LED. I can put that through a resistor. And then the other end of the resistor, I'm going to connect to ground. And so I've got output of the LED goes through a resistor, goes to ground. All right, and there's other ways you could do this, right? I could put my resistor over here, and I could run a wire from there to the resistor, and so on. So you can experiment. Let's put power on our chip also, right? So pin 7 goes to ground, 14 goes to VCC. Let's make those connections. So there's our ground line, and here's our power line, and that should power the chip. Alright, so if we ignore this top part of the diagram, we've built this so far. This is a complete circuit. This should do something if we run it, right? We're going to add this and put another LED on here, so that should do something also. But let's just look at this part right here. Let's see if it works. Okay, so let's start the simulation. And I've got 5 volts going in. My LED is off. My switch is open. When I close my switch, my LED turns on. The LEDs aren't terribly impressive. They should be really bright. But if you just watch the LED, when I slide the switch, it turns off, and then it turns on. Okay, so that's half of our circuit. Okay. And then if I wanted to continue doing this, right, just keep going. This output of pin 2 should go to the input pin 3. So take a wire, connect it between 2 and 3, and you've got this. And now pin 4 should go to the ground, the straight edge of another LED. So take a wire between pin 4, put your other LED in here and connect it to, in fact, connect it to that straight leg, and then the bent leg goes through a resistor to VCC. So take that leg, run it through a resistor, put the other end up to VCC, and you've got your complete circuit. And then you can flip your switch, you can see what the LEDs do when it's off or when it's on. You can also see how much current is being drawn, right? When the LED is on, I'm pulling 8 milliamps of current from the power supply. When the LED is off, I'm pulling 18 microamps from the power supply. Well, what is pulling power? If the light's not on, where's that power going?
The chip.
It's going to the chip, exactly. If I were to pull the chip out of here, my power draw drops to 0. So these chips actually take power. And you can find that looking in the data sheet also. That's what's inside your chips, by the way. right? Inside a 7404, this is what it looks like. There's the input, there's the output. It's a bunch of transistors and resistors. And you've got 6 of these things sitting inside that 7404. And so you can find electrical characteristics, voltage levels, and amount of current that's being used when the chip generates an output. You can also find, and we'll talk about this next week, we'll start talking about this, you can find how quickly these chips operate. Because when you change the input of an inverter from 0 to 1, the output should go from 1 to 0. But it's not immediate. Okay, it takes a little bit of time. So the change from the input A to the output Y, to go from low to high, if you want your output to go from 0 to 1, takes typically 12 nanoseconds. And worst case, 22 nanoseconds. To go from high to low takes typically 8 nanoseconds, worst case 15. So everything you want to know about this device is in this data sheet. And lots of things you don't want to know. Including a disclaimer saying you can't use this for like nuclear weapons and stuff, because they don't claim liability for that. All right, so hopefully that helps, right? With actually, you know, wiring a circuit from a schematic. And let me know if it doesn't, or if there's other questions on that. The other thing is, for Lab 2, you're making a schematic for Experiment 6. Okay? I would rather not, well, I don't want to see a schematic like this. Okay? This is useful when you're following instructions to build a circuit, but it doesn't really tell you what's going on. You have to look up U2, see that it's a 74HC32, find the data sheet for that, figure out what that's doing, right? So our goal is to go from, you know, some desire, some behavior we want, to a truth table, to a set of equations, to a circuit diagram, and then to a wiring diagram, and then to a physical circuit. Or, you know, a simulation of a physical circuit in TinkerCAD. So these things that you're seeing here, I gotta figure out how to unrotate it. There we go. These things that you're seeing here, these are wiring diagrams. This is sort of the last output of the design process before you actually build. But that's not what you're looking for in Experiment 6 of Lab 2. You're looking for something more like this. So your circuit diagram should have logic symbols, right? And switch symbols, and resistors, and ground symbols, and things like that. Okay? So make sure you build your diagram using this logical symbology. Okay? As opposed to, you know, a picture of the chip and which pins you're connecting wires to. Because that's hard for me to look at and figure out what the logic is. And your goal in Lab 2 is to design the logic for your circuit, not to actually implement it. Okay? So Lab 3, I think we actually implemented in TinkerCAD. But Lab 2, you're just coming up with a design. So schematic for your design, right? This is not a schematic, this is a wiring diagram. So punchline schematic, make sure you use logic symbols, okay, and 3-input OR, inverter, whatever. Okay, let me know if you have any questions about that. for the lab report, should we send a link to the experiments to it? Like a TinkerCAD link, I would say no, if that's what the question is. The lab report, I really just want to see, you know, for experiment 6, really just want to see a schematic diagram plus the other stuff, okay? So the intersection, inputs and outputs labeled, system diagram using the same labels and describing what ones and zeros mean. Truth table using the same labels and showing for all combinations of inputs what each of the outputs should be. And then a schematic that includes switches and LEDs. Okay. If you implement it in TinkerCAD, that's fine. That's a good way to sort of test your schematic, but that's not required for this lab. All right, so let me talk a little about minterms and some things that can help you with the homework. So let's just think about 3 variables. So let's just call it A, B, C. And we'll fill in our usual. Collection of input combinations, and we've got some function of A, B, C. And let's say our truth table looks like that. Okay, so there's a minterm associated with each of these. This is minterm 0, 1, 2, 3, 4, 5, 6, 7. And we can write out what each of those minterms is. So minterm 0 is A bar, B bar, C bar. This is A bar, B bar, C. A bar, B, C bar. A bar, B, C, and so on. So there's the 8 standard minterms. So if I wanted to write F, I could simply sum up the minterms where I want the output to be a 1. So I could say this is M2 plus M4 plus M6 plus M7. Which I could also write compactly as just the sum of minterms 2, 4, 6, 7. I suppose I want to write a Boolean equation for this. I want to actually write out the minterms. Well, I can fill out the truth table. I can find each place that there's a 1, and I can write the minterm that corresponds to it. Or I can maybe have a table like this already written in my notes and just look up the minterms. But there's a sort of trick we can use for writing down the expressions corresponding to each minterm. And here's the trick. Suppose we want to do minterm 2. Okay, we have 3-bit numbers. And on the first homework, right, I pointed out if you're doing a question with 8-bit numbers, make sure you always work with 8-bit numbers. Even if you can represent your number with fewer bits, if you're dealing with 8-bit numbers, write out all 8 bits. Okay, it's really important. It's important for 2's complement. It's important for what we're about to do right now. So the number 2 as a 3-bit number looks like this. Okay, that's the binary equivalent of the decimal number 2. Well, if I know that my input variables are A, B, C, I can write the product term that corresponds to this minterm just by looking at 0, 1, 0. I have a 0, I'm going to write A bar. I have a 1, I'm going to write B. I have a 0, I'm going to write C bar. Well, I just reproduced minterm 2. And the number 6, for example, is 1, 1, 0. So what's the minterm that corresponds to the 6th row of our table? Well, There's a 1 for A, so that's A. There's a 1 for B, so that's B. There's a 0 for C, so that's C bar. That's minterm 6, A, B, C bar. So fast forward to the homework. Let's say you have a question where you're trying to find f of A, B, C, D, E, F. And you want to write this as minterm 1 plus minterm 66 plus minterm 127. Well, you could fill out the whole 128 row truth table. You'd have 3 1s in it. You could look at the values for A through F in each of those rows and figure out what the product term is, but we don't actually need the truth table. We can write the number 1 as a 7-bit number, right? And just remember that our input order is A, B, C, D, E, F, G. And so minterm 1 is A bar, B bar, and so on, and G. And 66 is 64, 32, 16, 8, 4, 2, 1. And so minterm 66 is going to be A, B bar, C bar, D bar, E bar, F, G bar. And 127 is 7 1s, and so minterm 127 is A, B, C, D, E, F, G. So when you realize that correlation between the nth minterm, the nth row of the truth table, and the fact that the inputs there are the binary version of n, and then you know how to go from that set of inputs to your product term, right? This is a very direct mapping now.
So when I did this, I was
Mm-hmm.
trying to find a trick.
Okay.
Divide the first one by 2, figure out if it's going to be a 0 or a 1. But I couldn't find a trick for the other ones, so I ended up like generating a truth table online.
Okay.
Should I redo it this way?
So the trick of dividing by 2 is one way of finding what that first bit is, right? If your number's so if you wanted to find the second bit, right, you could do something similar, but yeah, go ahead and convert your number into binary, and then you can do it like this.
Okay, yeah, that makes a lot more sense.
Okay. Cool. All right, so keep that in mind when you're doing the minterm, max term problems. And remember, right, if you have like an MD5, it means that for the 5th row, that's a don't care. Okay. I've looked around online to try to figure out why it's MD, and I can't find an explanation for, how MD, what that stands for. That means don't care. I don't know. You can just think of it as like minterm dash or something. I don't know. But it means we don't care about that value, so it's a dash. All right, and you can go the other direction as well, right? If you had a product term like, A bar, B bar, C bar, D, E, F bar, right? What minterm is that? Well, if you have a bar, write a 0. If you don't have a bar, write a 1. This is minterm, sorry, that's a 1. This is minterm 6. Right, so there's this correlation between the product term itself and where it is in the truth table. All right, let me talk a little about some tricks related to K-maps, and then we'll go back and we'll work more with K-maps, and we'll work with them with product of sums, since we did sum of products Tuesday. So let's suppose we have a function of 4 variables, A, B, C, D. And remember the special ordering 0, 0, 0, 1, 1, 1, 1, 0. And I'm just going to lightly write down above each of these CD, 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 and AB correspond to these variables. Okay, so our truth table, each entry in our truth table corresponds to one box in our rectangle. So it's a one-to-one correspondence. And we're really just mapping our truth table into a visual representation. Like that. Okay, so there's some shortcuts we can use. Suppose we have an expression like A, B bar, C, D bar. And we want to know which box that corresponds to in our K-map. Well, this term corresponds to the case where A equals 1, B bar is equal to 1, so B is 0, right? So A, B, C, D. A is a 1, B is a 0, C is a 1, D is a 0. And we can look over here. Let's find a place where A is 1 and B is 0. That's right here. So somewhere in this row, and let's look for C equals 1, D equals 0. Well, there's a column where C equals 1 and D equals 0. So that's this point right here. So A, B bar, C, D bar corresponds to this. So if you're asked to simplify an equation using a K-map, and you're given an equation like, let's say F equals A, B, D, or B bar, C bar, D, and you want to simplify this, okay, one way to do this is to make a truth table out of this, and then do the usual K-map procedure. And that's great practice. Okay, so I would recommend doing it that way. Let me just show you a trick that you can use. So A, B, D, we're looking for any boxes in here where A is 1, B is 1, and D is 1. So A is 1, B is 1, that's everything in this row. And we want any boxes in here where also D is 1. Well, that's right here, D is 1, and right here, D is 1. So we can put ones in those two spots. That corresponds to A, B, D. We're reversing the process that we do at the end of a K-map. If we had a rectangle here, what would we do? We'd say A is 1, B is 1, C can be 0 or 1, so we ignore C, and D is 1, and we would write A, B, D. And if we want a rectangle corresponding to B bar, C bar, D, well, we need B equal to 0, C equal to 0, D equal to 1. So B equals 0, that's either this top row or this bottom row. And then we want C equals 0, D equals 1. Well, that looks like this column right here, C equals 0, D equals 1. So anything that's in either of these rows and also in this column, well, that's just this box and that box. And if we, had a rectangle covering those two boxes and we try to write the product term corresponding to it, we would say, well, A can be 0 or 1, doesn't matter. B is 0, so we would write B bar. C is 0, so we'd write C bar. D is 1, so we'd write D. So if someone gives you an equation like this and says simplify it, without writing a truth table, you can fill in the ones in a K-map, and then you can make coverings. So I could cover these, and I could cover that. And that's going to get me back to where I started. But if there were some other things and I could cover these with bigger rectangles, then I would get a simpler expression out from doing this procedure. Okay, the other thing I want to look at is, let me just redraw my K-map here. And these are tricks or observations. They're not things I want you to memorize. Okay, the discussion that we've already done and that I posted on the video of K-maps, that's really the explanation of what K-maps are and how you use them. But these are tricks, right? So as you're doing stuff in school, your mind is always working. It's trying to find shortcuts, trying to find explanations, right? So things you can do, divide the first digit and you know, simplify your truth table like that. So I'm just showing you some tricks here, okay? So if we look at these minterms, and let me just write out these numbers. All right, minterm 0 corresponds to all the inputs are 0. That's this box up here. That's minterm 0. 0, 0, 0, 1, A and B are 0. C and D should be 0, 1. That's right here. 0, 0, 1, 0, 0, 0, 1, 0. That's right here. And 0, 0, 1, 1. That's there. So our first 4 terms of our truth table go here, 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 and there. Our next 4 terms are going to be exactly the same, except A, B are 0, 1, so they're going to be sitting in this second row. So this is M3, M4, M5, M6. Our next set of terms are exactly the same order, except A, B is 1, 0, and that's down here on this bottom row. So this is M7, 8, 9, and 10. And then our last 4 entries, A, B, are 1, 1. That's this third row. So this is 12, 13, 14, 15. So after you've done a few hundred of these K-maps, you start to see a pattern. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Nobody called me on this. This is supposed to be 4, 5, 6. 4, 5, 6, 7. There's head 3 up there. Oh man. Let me just redraw that, because I made a mess of it. Okay, these are minterms. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you're asked to simplify an expression, which is the sum of minterms 1, 3, 2, 10, 5, and 7, right? You can just come right here and you can put a 1 here, put a 1 there, put a 1 there, and 5 and 7. And now you can just go to town, draw a rectangle around that, draw a rectangle around that, write the corresponding product terms, and you're done. Alright, so just shortcuts and tricks that you can use there. Alright, so yeah, let's talk about the don't cares. So the don't cares are going to be dashes in our truth table, and we are going to carry those into our K-map. So I actually have a student who made me a rubber stamp out of this. He 3D printed a rubber stamp that makes this version, this piece of a truth table, so that I didn't have to keep writing this, which was pretty cool. It's locked in my office somewhere at Clark. I forgot to bring it home before quarantine started. So I gotta write these by hand. But you know, the more you write this, the better you get at it. So here's A, B, here's C, D. And always number your edges. If you try to do it in your head, there's a better chance you'll forget about the special ordering. Okay, so let's fill in some values here. 0, 0, 1, 0, 0, dash 1, 0, 1, and let's say we don't care about any of these. Okay, if I carry over the ones, this corresponds to a 1 right there, this corresponds to a 1 right there, and this 1 corresponds to a 1 right there. No, it doesn't. Corresponds to a 1 right here. 1, 0, 0, 1. Okay, so if I try to cover this, I've got 3 1x1 rectangles. I'm just going to get plain sum of products. No joy there. If I fill in these dashes, I've got a 0 dash 1, I've got a 0 1 dash dash, and then I've got dashes here. Well, now I can go to rectangle town, right? I need to cover the ones. I don't need to cover the rectangles, but I'm allowed to cover them. So first thing that jumps out at me is this one right here. I can cover that with a big rectangle, right? Big rectangles will be simpler terms when we write the sum of products. And then this one right here, I can see another rectangle containing 4 squares. And then this one down here, there's another 2x2 rectangle I can use. Right? So whereas before I had a sum of 3 products where each product had 4 terms in it, I'm going to get something a lot simpler here. This rectangle over here, A can be 0 or 1, B can be 0 or 1, so they don't appear. C has to be a 1, D has to be a 0. This lower 2x2 rectangle, A has to be a 1, B doesn't matter, it can be a 1 or a 0. C can be a 0 or 1, doesn't matter, and D has to be a 1, so that's just AD. And this top rectangle, A can be 0 or 1, B has to be a 1, C can be a 0 or 1, and D has to be a 1. And so that's just BD. So it's a much simpler expression. I didn't use this dash, right? I don't have to. Since I didn't cover it, what it means is in the final equation, this will end up being a 0. But that's okay because I said I don't care about it. Right? I don't care what the value of that is. The ones that I do cover, those will end up being 1s. So the dashes just give you more options for covering, which you know, your goal is a small number of large rectangles. So the dashes can help you do that. All right, let's do an example with 3 variables, just for comparison. So you've got a choice of how you draw a K-map for 3 variables. You can do it like this, or you can do it like that. And it's not going to affect the final outcome. It's totally your choice. You also have complete choice over how you label the individual cells. I always put these in a way that's in the same order as what's in my truth table. That's just how I've developed a habit of doing it, and so it lets me know some shortcuts. But there's nothing magic about, you know, putting A over there. I could do B, A, C if I wanted. But habits are usually helpful. All right. So there's ways that I would do 8-row truth table. And if we just think of these as minterms 0 through 7, and we just fill these in using our minterm representations, this is minterm 0, minterm 1, 2, 3, 4, 5, 6, and 7. So 1, 0, 1, A is 1, B and C are 0, 1, that's right here, there's minterm 5. And in this format, it would be minterm 0, 1, 2, 3, 4, 5, 6, 7. And let me stress, there's nothing to memorize here, okay? This is not stuff that you need to memorize. This is not stuff you need to have on your sheet of notes. This is all stuff that you can get by doing what we did Tuesday with K-maps, which is, you know, take each of these and look up, okay, so minterm 2 would be right here, and A is 0, B is 1, C is 0. So A is 0, B is 1, that's right here, C is 0, that's right here. This is where minterm 2 goes, right? You can find this, you can create this from thin air just by knowing, you know, that minterm 2 is row 2, 0, 1, 2 of the truth table, and so on. Alright, so that's the deal with don't cares, that's the deal with things that aren't for variables, right? And, you know, a simpler case is a function of two variables. Well, our K-map here is just going to be a 2 by 2. So let's say this is A and B. And suppose we had a truth table like this. Well, 0, 0 goes right here, 0, 1 goes right here, 1, 0 goes right here, 1, 1 goes right here. I know I said don't fill in the zeros, I just filled in the zeros by mistake. But we would cover this with rectangles, and there's a rectangle that covers all our 1s. And what does this correspond to? Well, A doesn't matter, and B has to be equal to 1. So this truth table just corresponds to the function f of A comma B equals B. And you know what? If you look at this, whenever B is a 1, f is equal to 1. And whenever B is a 0, f is equal to 0. So yeah, this is the truth table for f equals B. And we found that by using a K-map. Well, let's use a function of two variables to look at a badly behaved type of K-map. Actually, let's go ahead and take a 5-minute break. And then we'll come back, we'll talk about this, which is going to be about XORs, and then we'll talk about product of sums. So let's chill for about 4 minutes and come back around 1 o'clock, and we'll continue this. Alright, I'm back here. Hey, has anybody else had their car battery die through all of this stuff? Because I went to go to the store yesterday and my battery was dead. And this actually happened before recently. So the guidance I saw online was try to drive 20 minutes twice a week to keep your battery charged. I drive about 10 minutes once a week. Some other people. I was driving 10 minutes once a week to go to Freddy's for groceries. So yeah, 20 minutes twice a week is the guidance I saw. So if you haven't driven your car in a while, go drive it, get a jump, and then drive it regularly. Or you end up getting a new battery tonight like I do. But I had an old battery anyway. Alright, so continuing looking at these kind of unusual cases. So let me just pick on a 2 input. And suppose this is the truth table for our 2 input function. We can make our K-map. And if we put the 1s in here, while A is 0, B is 1 is right there, and A is 1, B is 0 is right there. And this is, the really sad case, because no matter how clever we are, the best cover we can find is just a 1 by 1 rectangle around these. And if we had a function of 3 variables, the worst case would be something like this, right? Or flipped around, right? And if you have a function of 4 variables, the worst case is whatever checkerboard pattern you get from that, right? You got 8 terms, and each of them you can only cover with a single 1 by 1. So even with a K-map, your simplified expression is just a plain old product of sums, and it's a lot of logic, and it's really unpleasant to build. So just looking at this top case, ignore those. If we were to write f in terms of sum of products, right, f would be a bar b or a b bar. Okay, but there's another expression for f having this truth table. Does anybody know what that expression is? Or logic function? So this is an exclusive OR. And this truth table almost looks like an OR. If we had a 1 down here, that would be an OR. This is a 0, but an XOR is basically like an OR, except only one of your inputs can be 1. So in the case where both inputs are 1, it's a 0. So this is the K-map of an XOR. And if we saw a K-map with this checkerboard pattern, it would take, 2 AND gates and an OR gate to build it as a sum of products, but we could also use a single XOR gate, and that'll get us the same behavior. And if we had 1s here and 0s there, that's an exclusive NOR. It's just the complement of this. And if you have this kind of pattern, where you have the checkerboard on a 3-input function, that's also an exclusive OR. That's actually going to be something like a 3-input exclusive OR. So we'll come back to looking at exclusive ORs in a couple of labs when we talk about adding circuits, right? Circuits that do addition, and what it means to XOR 3 variables, because it's not really a 3-input XOR, but there's a way we can define XOR of 3 or 4 things, and it corresponds to these checkerboard patterns. So when you're designing circuitry and you're coming up with K-maps that have this kind of thing where you end up with these small rectangles, there's a possibility you can use an XOR to get a simpler circuit. So we'll dig more into that as it comes up. So all of this that we've been doing so far is about sum of products. So let's flip it around, and let's look at product of sums and K-maps. Someone must sell a notebook somewhere just filled with pages of this that you can just fill in. It's probably on Amazon somewhere. So product of sums, right? These tend to work well when we have lots of zeros in or lots of 1s in our output, right? So let's suppose we wanted to do a function like this. Alright, as a sum of products, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 1-terms, right? So 11 products that we would sum all together. And when we put this in the K-map, right, for a sum of products representation, we transfer the 1s over to here. If we want to do product of sums, So product of sums. We transfer the zeros into the K-map, and we don't transfer the ones. So we have fewer zeros. We only have 5 zeros. So 0, 1, 0, 0. That's a 0. 0, 1, 1, 0. That's right there. 1, 0, 1, 0. So 1, 0, 1, 0 is right there. 1, 1, 1, 0. 1, 1, 1, 0. And 1, 1, 1, 1. That's right there. All right, we make the same covering with rectangles. It's just that we're covering the zeros and the dashes instead of the ones. But the covering procedure is the same. The rules are the same, right? Use as few rectangles as possible. Use as large of rectangles as possible. So I'm going to draw a rectangle here, and I'm going to draw a 2 by 1 to pick up that 0 over there. And then I'm going to split a rectangle up here to pick up these two. Right, so there's my split of a rectangle. And then let's look at the sum terms that correspond to each of these boxes. So this box down here, let's look at the values of A, B, C, and D. So we've got these two rectangles here. A is a 1, A is a 1, A's got to be a 1. B is a 0 here, it's a 1 here. We're not going to worry about that because B takes on both values. C is a 1 and D is a 0. Alright, so that corresponds to a sum term where we write the sum terms the same way that we wrote max terms. So since A is 1, we're going to write A bar. Since C is 1, we're going to write C bar. And since D is 0, we're going to write D. And we're going to OR those together. And so that's the sum term corresponding to that first box.
So should you overlap boxes to avoid having like a term in its own box?
If you can avoid having a single term by itself by overlapping, yeah, definitely overlap. Right, so I could have just done a 1 by 1 here, but that would have given me a sum term with 4 elements in it. So yeah, get a bigger rectangle by overlapping.
Gotcha. I was avoiding overlap.
Okay, no, the overlap is good. It usually means that things are going well. Alright, so this box right here, A is a 1 in both boxes, B is a 1 in both boxes, so A equals 1, B equals 1. C is a 1 over here, and it's a 1 over here, so C is 1. D is a 1 here, but it's a 0 there, so D doesn't matter. So this is going to be the term A bar, or B bar, or C bar. And then the split rectangle, A is a 0. So since A is 0, it's going to be an A. B is a 1, so it's going to be B bar. C is a 0 here and a 1 here, so C doesn't matter. D is a 0 here and a 0 here, so D is 0 everywhere. So that's just going to be D. And that's the sum term corresponding to that rectangle. So our expression for F is now A bar or C bar or D ANDed with A bar or B bar or C bar ANDed with A or B bar or D. And that's your simplified expression. And it's a product of sums, right? These are sums and we take the product of them. Alright, other questions on this? So I go through this in that video that I posted the other night, and it's in the textbook. Other questions? All right, well, let me, all right, so we're basically done with chapter 2, which ends with XORs. So make sure you read through chapter 2. And then chapter 3 goes deeper into this and starts talking about something called glitches. And I'm not quite ready to talk about those, so I'm going to go down here to this beyond standard logic and talk a little about this. And this is stuff that you'll see in an upcoming lab also. So here's some more stuff. This is section 3.3 that talks about designing logic circuits. So this is this idea of having a component ID block up here, which lists an ID for each chip, a description of it, right, the part number, where you want power, where you want ground, and which pins aren't connected to anything. And then on that chip, in your logic diagram, you go ahead and you list the pin numbers. Okay. And down here you can put a description of the project and your name and the date and so on. There's a good template for it. Fan in and fan out is just when you're dealing with physical chips. You can take the output of an inverter, you can connect it to an LED and drive the LED. You could take the output of an inverter and connect it to 100 LEDs, and it's not going to light those LEDs up because these chips only put out a certain amount of current. And to light an LED takes like 5 milliamps. And if you had 100 LEDs, you'd need 500 milliamps to light them. And a simple inverter or AND gate can't put out 500 milliamps from its output. So there's a reality that the output of a gate can only drive so many things, including inputs to other gates. Okay, so this question of how much can a gate drive, it's called the fan out. And if a chip says that the gate has a fan out of 5, it means you can drive 5 inputs with it. Okay, and if you need to drive more, you need to do something to increase the current of that signal. It's not going to come up in TinkerCAD. But when you're dealing with these chips in an actual lab, just know that there's a limit to how much you can connect these things. So for example, typically we might have an inverter, right? So we have some signal A coming in and we have the inverse of A, and that might feed a few gates. Well, can this one output drive 3 gates? Yeah, probably. Can it drive 10 gates? Probably not. So you need to look at this part and see what its fan out is, and if it says the fan out is 6, you can drive 6 inputs. And then you are trying to pull too much current after that. So that's what fan out is. This section is just talking about the fact that you can build anything you want from NAND gates, and this is what we did the first week, right? From a NAND gate, here's an inverter. From a NAND gate, here's an OR, and so on and so forth. So the computational completeness of NANDs and NORs. I don't feel like talking about compressing truth tables right now, but we will talk about that next week. And I'm not going to talk about that. So I want to talk about this. Most of the devices that we use in this class are simple logic gates. Okay, 7404 is a package of inverters. 7408 is a package of AND gates. 7474 is a package of what we call flip-flops, which we'll talk about in a few weeks. So mostly they're pretty simple functions, right? They're building blocks of other larger circuits. But there are some chips that we will use that are more complex. Okay, one of them is called the 555, and we'll use this a lot in this course, and this works in TinkerCAD. The 555 is what's called a timer chip. It's a chip that we can hook up some resistors to, as well as something called a capacitor, which we might touch on in 120 depending on the class. but we don't really work with. But by hooking these things up in a certain way, we can cause the output of this chip to toggle between high and low. And so we can use this like a function generator. We can have it generate a logic 1 signal every second if we want, and then generate a logic 0 signal for a second, and it'll keep doing this, just toggling between 1 and 0. It's a really, really useful chip. It's one of the most useful chips ever created. You can find a lot of interesting history about this chip. It was started by somebody who thought it would be cool to make a chip that did all this. And he talked to his boss, and his boss was like, no, that's ridiculous. There's no reason to do that because you can do it with, just a few chips that already exist, just putting them together. But he really wanted to make one chip that did this. And so he went ahead and did it anyway, and it became like, the best-selling chip that this company had ever made. So that's a really useful one. We'll use that a lot in this course, and we'll also use it in Engineering 270, the microprocessor course. And there's chip. Say again?
How fast can it toggle?
Pretty quickly. I mean, definitely megahertz range. Nothing up to gigahertz. But it'll go, a few million times a second, not a problem. And there's actually a formula you can use for how long it'll stay high and low. So if you add up your resistors, multiply by your capacitor, and multiply by this magic number, that tells you how long it stays high. So the typical arrangement we use, RA and RB are both a megahertz, mega ohm, and C is a microfarad. And so it's 2 million times a millionth. This is about 2 times 0.7. This is about 1.4 seconds it'll stay high, and 0.7 it'll stay low. But if you make your values a lot smaller, you can get millisecond or microsecond high and low times. And they're dirt cheap, right? This was one of the things at the time when this chip came out. Standard chip cost $5. They sold this for $1 a piece, and nobody had ever seen an integrated circuit you could buy for only $1. And so it was just an instant hit. The person who designed it, the first week, he said his phone never stopped ringing, and he was getting all these calls from engineers who were just so excited with what they were doing with this chip they wanted to tell him about it. And they were coming up with applications he had never thought of. It was just the right time, the right combination of things. And it's just a little 8-pin chip, and but it's really powerful. And now they cost fractions of a penny or something like that. But at the time it was a big deal. So there are chips called encoders, and there are chips called decoders. And I'm not ready to talk about these either, but here's what's inside this encoder, right? It's a bunch of circuitry. It's basically doing a sum of products, right? Although these are AND gates, right? So there's the products, and here's the OR gate. That's the sum. And so if you look at the data sheet for this, you'll find the truth table. And if you were to write out the sum of products for the outputs, A0, 1, and 2, right, they would correspond to this wiring. And this is, inside one chip. Instead of having to build this, you just go get a 74-148. So that's a an encoder. This is a decoder. And we will talk about these probably next week. I'm just kind of giving you a high-level view for now. They're truth tables that are particularly useful for various reasons. Okay, and we'll be using them in our lab, so we'll see some practical examples. This is what's inside this chip, a little simpler. This is a 7-segment decoder, and we do have 7-segment chips on TinkerCAD, so we'll play with those, and we'll use this chip to drive it. And that's got a very complex truth table and a very complex circuit that goes along with it. Okay, having this chip available means you don't have to build all this on your proto board, which is useful. Okay, what I do want to talk about is programmable logic devices. So we know that we can take chips and we can put them together and we can get different behaviors out. Okay, And we know that when we want to draw a diagram, let's say we have an equation like F equals A B bar C or A bar B or ABC. Alright, if we wanted to write a circuit diagram to implement this, there's this procedure, right? Take your inputs, run them vertically along your page, and put an inverter next to each one to give you the complement of that. And we're writing this because we know about sums of products. We know that the product terms sometimes have our variables and sometimes have our variables with a bar on top. Well, once we do this, this line represents A, this represents A bar, B and B bar, C and C bar. And we know we're going to do products. We're going to have AND gates. Depending on how many products we might have a bunch of AND gates. And we know we're going to have OR gates. And depending on how many outputs we want to generate, we might have a bunch of OR gates. So this is kind of a template for a schematic diagram for an Engineering 250 circuit. Now suppose this is the equation I want to make a circuit diagram for, and suppose I already have this page sitting here in front of me. I've like copied this, I have hundreds of these pages, right? So I pull one of these out and I say, okay, I want my output to be F. Okay, so I'll label that F. I want to OR three things together. Okay, so I'll take the output from this gate, and the output from this AND gate, and the output from this AND gate. Okay, what should the inputs to this first AND gate be? I want one of the inputs to be A. Okay, I'll draw a wire over to A. I want the next input to be B naught, so I'll draw a wire to there, and the last input to be C. And my second gate, I want to do A bar ANDed with B, so I'll draw a wire over to A bar, and I'll draw a wire to B. And my last input, I want the AND gate to be A, B, C, so I'll take this AND gate, connect one input to A, one to B, one to C. And now I have a beautifully drawn schematic diagram for my circuit that generates this equation. And all I had to draw was a few wires and a few dots. Okay, you still with me? So this stuff is always going to be there. I didn't have to change that. So let's make this even more general. I hope whoever invented the eraser got like a lot of money for it, because erasers are awesome. They probably didn't. Okay, I'm going to make a few more permanent additions to this. I'm going to run a set of wires over here, and a set of wires over here. I probably only needed 3 wires for each of these, so I'll just go ahead and do 3. And so on, right? I could keep doing this. And I'm going to run some wires into my OR gates. Now, when you draw a schematic on a 2-dimensional piece of paper, it's hard not to have wires cross each other. It's inevitable, right? Because sometimes that's just how the geometry works out. So when wires cross each other, we don't assume that they're connected. What we do is if we have wires crossing and we want to indicate that there's a connection, we draw a little circle where they cross. So right now there's no connection between this wire and that wire. Okay, they're just wires that happen to be crossing each other, just like on a protoboard, two wires might overlap, but they're not connected, right? Okay, now suppose this is my template and I want to implement a circuit diagram for this function. All I gotta do is add a few dots. Okay, here's my output F. I want it to be the sum of three product terms. Okay, here's gonna be my first product term. I want A, B bar, C. So I'll connect this line to A, I'll connect this to B bar, I'll connect this to C. And this input we'll just ignore. The second term I want to be A bar B, so I'll connect one input to A bar and the second input to B. And this gate I want the inputs to be A, B, C, so I'll connect one input to A, one to B, one to C. And then I want to OR these three outputs together, so I'll feed this to one input of my OR gate, this to the second, this to the third. And I am done. And by just drawing a few dots on this template, I've given you a schematic diagram for how to implement F. And if I really meant, you know, that this should be A bar BC, well, that's not a problem. I'm just going to change this dot from where it was to right here. You got a totally new function now. Alright, so this is a cool concept, right? The idea here is that we can create a schematic by just indicating a few connections. Right? Just indicate where you want these horizontal wires to connect to your inputs or inverted inputs, and where you want these vertical wires to connect to your product terms. Now, if we could do this in a physical piece of hardware, if we could somehow have all this stuff, you know, already available for us, and then physically come in and just make a connection where certain wires cross, building these circuits would be a lot easier. If you remember from 120, building a circuit on a protoboard is kind of a lot of work, right? If we could just somehow indicate where the connections are, life would get a little easier. Well, we can do this. So there are devices called Programmable Devices that basically look like this internally and let you from outside specify where you want connections to be made. Alright, so there's a question on homework problem 11. It says, what does SAR mean? So SAR is systematic algebraic reduction. And we have not gone over SAR, and I'm not asking you to use SAR for that question, but you can read about it in the textbook, and it's a way to algebraically simplify an equation. Alright, so this is programmable logic. So the last part of this chapter 3 talks about different kinds of programmable logic. And the way that you implement this, or at least the way we used to implement it, was with fuses, right? So if you have an older apartment, your electrical wiring is protected by fuses, right? It's a small piece of metal that all the juice going to your power outlets and your lights and your stove and so on runs through this little tiny piece of metal. And this little piece of metal, if you try to put too much current through it, it will melt. And the idea is if you plug too many things into the wall outlet, you know, you get extension boxes and so on, and you try to draw too much current, the wires in the wall might overheat and melt or catch fire. So you put a fuse in line with that, and the fuse will melt before the wires in the wall melt. And when the fuse melts, it doesn't conduct electricity anymore, and so you've protected the wiring inside the walls. So imagine if we had a fuse connecting every horizontal line with every vertical line. Okay, just a little piece of metal that connected these together. And then from outside, if there was a way to come in and push a bunch of current through the fuses that you wanted to get rid of. So we'd start off with fuses everywhere. And we'd come in and we'd blast a bunch of current through a set of pins that basically make this fuse melt. So we break the connection between this line and that line. And we melt all of these fuses, and this fuse, and that fuse. And we melt all the fuses except at the spots where we want a connection. And when we're done, here's the circuit that we've got, right? We've got something that implements our actual function f. Now we don't use fuses anymore. We use, quantum effects and things like that. But we still talk about it in terms of fuses and fuse maps, okay? And this would be considered a fuse map. It's basically showing where we want connections between the horizontal and vertical. And we can view our device as having two sections. There's, guess I should put it here. There's a section over here which we call the AND plane, right? Because these fuses control the inputs to the AND gates. And then there's a section over here which we call the OR plane. And the OR plane controls the connections from the product terms to the inputs of the OR gates. So two separate pieces of this programmable device that we can configure, the AND plane and the OR plane. Well, in some cases, the AND plane is configurable and the OR plane is not. Okay? If the AND plane can be configured and not the OR plane, that's called programmable array logic, or PAL. Okay? The OR plane connections are fixed at the factory. The AND is programmable with fuses. That's programmable array logic. The flip side of that is where the AND plane is fixed and the OR plane is programmable, and that's called programmable read-only memory, or a PROM. And the sweet spot is both of those, where you can program both the AND and the OR connections, and that's called a PLA, programmable logic array. And there's no intuition that I can find for why this is a PLA and this is a PAL. Programmable logic array versus programmable array logic. I don't know where those terms come from. I think one of them just came first. But anyway, that's what those terms mean. So when we draw our pictures, we use a little dot to indicate that that there's a fixed connection, right, from the device from the factory. We draw an X where we want to make a connection, and we have just a crossing where there's no connection. So if this was a fuse map, right, where we could program both the AND plane and the OR plane, I would actually indicate these with X's. And I would indicate these with X's. But if this came from the factory and only the AND plane was programmable, right, then the OR plane would look like this. Right? And these connections are always here. And I only get to control what the products are that get summed together. Another thing to note about this is we don't need to do simplification, right? In fact, there's almost no such thing as it, right? A bar B, well, if that was actually A bar B C, right, I could just, have another connection here, right? So this is a really fast way to implement logic equations in hardware, and we have software programs that will do this for us, that will take a truth table and figure out what the fuse map should look like, and will automatically program these devices. All right, some of these devices can be reused. Now, if these are actual, metal fuses that we're melting, once you melt a fuse, that's it. There's no connection between, say, this line and that line. There's no way to get that connection back. But like I said, we don't really use fuses anymore. We use more, bizarre stuff that's based in quantum physics and such. And with this newer technology, it's possible to replace these fuses once you've blown them, right? To restore these connections. So we can do what's called erasing the device. Okay, so that we can put it back to its original factory state where all the connections are intact, and then we can get rid of the ones that we don't want. Right. So I should mention, right, because these are actual fuses that are being melted, right? Once you program this device, it stays programmed like that forever. You don't have to keep it connected to power. You can take it away, and you can pull it off a shelf 5 years later, and it still implements the same function. Okay. Same thing with these other technologies that are used to implement this. You program it, and then you can come back to the device later, and it'll still have that same programming. But you can erase some of these devices, and they're typically, the old versions used to be erasable using ultraviolet light. And it's worth looking at pictures of some of these things, right? So these devices would have a little window on the top, right? And that window was usually made of quartz, so it would let visible and ultraviolet light pass through it. And then you would get a device called an eraser, different kind of eraser. That's not a very good one. This is a good picture, right? And you would put your chips in this little tray, and you would close the door, and you would set the timer, and it would take about 30 or 40 minutes. And when the timer expires, this chip would have been erased. And it's back to an empty piece of logic with no programming in it. And then you could hook it up to your programming device, and you could load in a new set of equations. So those were erasable programmable devices. And now we have electrically erasable programmable devices. So you can erase them simply by hooking them up to a piece of equipment, and it will send information into the chip that causes it to reset all of the connections, and then you can reprogram it. And this is not totally dissimilar from what we do with solid state drives or flash devices or things like that. It's similar technology, right? We can load values into those. It will remember the values for a long time, and we can recover them whenever we want. So you can look through this part of the text, right? This is chapter 3.9, and there's just examples of what we've been talking about. And you can buy these devices for a few bucks, right? They're not that expensive, and they're pretty powerful if you just want to implement some logic. A whole lot easier than wiring up a proto board with lots of wires and chips and things like that. And they're lower power, they're more reliable, they take less space, etc., etc. So it's a really good technology. And this is, a very simple design. It's strictly doing a sum of products. But some of these also have the ability to have feedback. So the output can actually be sent back in to act like another input. So that means we can build circuitry that might look something like this. Here's an input A, and it goes into an AND gate, and maybe this goes through an inverter, and this goes into an OR gate, and maybe this goes into another AND gate, and maybe this goes back into here. Well, this is interesting because the value going into here depends on the value coming out of here, which depends on the value coming in here, which depends on the value coming out of here, which depends on this value coming in here. So we have feedback. And this is going to be our next topic of discussion. But let me leave you with a few cases to think about. So what is the value over here where the question mark is going to be? Is this going to be a 1 or a 0? Well, suppose it's a 1. If this value is a 1 right here, that 1 is going to go to the input of an inverter. The inverter is going to change it into a 0. And so now this value is going to be a 0. Well, if this value is a 0, that will feed into the input of the inverter, and the inverter will change it into a 1. And so now this value is going to be a 1. And of course, if it's a 1, you're going to get a 1 on the input, you're going to get a 0 out here, you're going to get a 0 out here. So if we call this output x, and we looked at x across time, we're going to see something like this. It's going to toggle between 0s and 1s. Because as soon as it becomes a 1, the input of the inverter is a 1, the inverter is going to change its mind and output a 0. And that's going to go into the inverter, and it's going to change its mind and output a 1, and so on. Now this won't actually work if you build this in a lab. I don't know if it works in TinkerCAD or not. That'll be fun to try. But this will work in a lab. If you actually build this circuit and you look at the output on an oscilloscope, you'll see a really sloppy square wave. And it's about, 9 or 10 nanoseconds from one peak to the next. So it's about a 100 megahertz oscillator. But here's the more interesting case. What happens if we have a circuit like this? What's the output of that circuit going to be, a 1 or a 0? And we don't know. It really depends on, what's happening in the universe at the moment that we put power onto this board. But here's what we do know. It could be that x is equal to a 1. And if this is a 1, that's going to go into the input of an inverter. The inverter will output a 0. And a 0 going into this inverter will output a 1. And so if x happens to be a 1, it's going to stay a 1. But the other possibility when we turn this on is that x could be a 0. And if x is a 0, then the input of this inverter is a 0, which means the output is a 1. And if you have a 1 going into an inverter, the output of that is a 0. So depending on what the original value of x is, it's going to stay at that value. But we don't know if it's going to start off and stay at a 0 or at a 1. Now that's a little weird, but it turns out to be extremely useful. Because if we have a way to force this output to be, say, a 1, it'll stay a 1 forever. And if we have a way to later come along and force it down to a 0, even for just a moment, it'll stay a 0 from that point on. So what are we describing? We're describing a memory. And everything we've done with digital logics up to this point, and everything we did with digital logics in 120, is only one piece of the story. Those are ways that we can take inputs and turn them into outputs. But all those circuits we've built, they have no memory of what's happened. Their behavior depends strictly on the inputs. Once we can make a memory, we can create an entirely new class of circuits. Circuits whose behavior depends not only on the inputs, but also on what's happened in the past. And having memory in our circuits, that's why we can have computers and phones and music players and everything else that constitutes our technology-driven world. So memory is really the key. And this is really the beginning of a memory circuit. So next week we're going to expand on this. We're going to explore all kinds of ways of storing information in a digital circuit. And some of them are going to be no more complex than just two gates. But two gates put together in very particular, very clever ways that will let us store ones and zeros, remember them, and then use those values later. So that's going to be the next part of the course. All right, so keep plugging away on the homework and the labs. Office hours tomorrow if you have questions. Email to some degree, I'm available there. Let me know how things go. Have a great rest of the week and weekend, and I will see you next time.
Have a good day.
Thank you, you too.
Bye.
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 Bye.